It's important to remember that your outline for your research topic is due at the end of this week. So just really like a bulleted form of your abstract. It doesn't have to be in paragraph form written up. It just needs to kind of give us an idea of your topic, your subtopics, how are you going to introduce it? How is it relevant? That kind of thing. Next week, you need to have your rough draft submitted to Erina so that she can look it over, get second eyes on your work. And so just to keep you guys moving along, the sooner you get the abstract draft to her, the better, because then she's not swamped with a bunch of them all on the last hour. So if you have something written up, the sooner you get that to her, the sooner she can give it back with feedback, and then you can, move forward to your final draft. Okay. All right. Let's dive into it, shall we? Let me find my slide. Hold on just a second. Yeah, that's it. Okay.
Have you looked through our topics at all, just to kind of make sure we're on the right track? Or,
Yeah.
I think my topic's good, but I kind of have this worry that at the last minute it'll not be relevant enough or something, and I'm gonna have to start all over.
No, I mean, unless you heard from me, your topic is fine. I was pretty lenient this quarter on the topics. When we get into Chem 103, then, we up the ante a little bit, and we'll have to scrutinize the topics a little bit more. But for this, since we're getting our feet kind of wet, I was pretty lenient, so I wouldn't worry about it unless you've heard from me, which you haven't, saying otherwise. Okay. But good question to ask. Okay. So what I'm going to do is, looks like that date is wrong. Yes, because I was planning on doing this earlier, but I want to just kind of quickly go through some of the concepts that I had discussed in the entropy lecture last week. Just kind of breeze through that to brush you guys back up on it, and then we'll hop into the new stuff. Okay. So I introduced the second law of thermodynamics, and I said that it was that simply that spontaneity causes an increase in entropy. Okay. So as spontaneous processes occur, entropy goes up. And we said that entropy is like the randomness of the universe, right? Random processes. It's also considered disorder of things. And that spontaneous processes are those that proceed without outside intervention. So the nail rusting is spontaneous, but to get a rusty nail and turn it back into a shiny nail, that would not happen spontaneously unless you gave it, of course, an infinite amount of time. Just like in this example here, if you have two different bulbs that are separated by the stopcock and all the gas is in B, and you turn the stopcock and you let it go into and equalize between A and B, it's not going to go back into B as a spontaneous process. You would have to have some kind of outside intervention to force that all into the B flask and evacuate the A bulb. Okay. The nail rusting is a spontaneous process, but to take that rusty nail and turn it back into a shiny nail, you would have to have outside intervention of some form, and then that defines it as a non-spontaneous process. And then we said reversible processes are those in which you can go back in the opposite direction by simply repeating the steps in the reverse order. Okay, and we said that phase change is a good example of a reversible process, because if you take heat out, then you change enough heat, you can change the phase from a gas to a liquid or a liquid to a solid. And the process was removing heat, leaving the system into the surroundings. So if you just were to reverse that and take that heat that was taken out into the surroundings and put it back into the system in the same amount, you reverse the process, and this phase change goes from either a solid to a liquid or a liquid to a gas. I said that irreversible processes cannot be undone by exactly reversing it. So unlike a phase change, if you had a system where you had this chamber and it was separated by a movable partition, and on one side you had a vacuum and on the other side you had the gas, and you lifted that partition up, the gas would then diffuse and equalize throughout that chamber, right? And you have equilibrium. Now, if you wanted to reverse that, you would have to do the same steps backward, and that would be just to move that partition back down. But that wouldn't create the initial system where you had a vacuum on one side and a gas on the other. You would have gas on both sides. So in order to get back to that initial state, you would have to put work into it in the form of a piston to push the gas to one side. And so therefore it's not reversible, it's irreversible because it requires outside intervention. Okay? Entropy is the randomness of the system. And just like enthalpy and just like enthalpy, entropy is a state function. So it doesn't matter the stuff in between. If you want to calculate the change in entropy, all you need to know is the final entropy value and the initial entropy value. And that's what we'll get into, later on, calculating entropy. We take the entropy of the products and the entropy of the reactants, and we subtract them to get the overall entropy, just like we did for enthalpy. Now, entropy we designate as S. So the change in S is equal to a reversible heat over temperature. Okay. Again, this is when heat is, or a process in general is reversible. Okay. Now, phase change, as I mentioned, can be reversible, right? We can just backtrack the same steps to get back to the initial phase that it was in. Okay. And so this was a concept for the ICA this week, showing that for reversible processes, we can say that the change in entropy of the universe is equal to the sum of the change in entropy of the system and its surroundings. And then we can set that all to 0 if it's reversible. Okay. If it's irreversible, then it's spontaneous and entropy is going to increase. So we say that the change in entropy of the universe is equal to the change in entropy of the system and the change in entropy of its surroundings. And that is going to be greater than 1. Okay. So for all spontaneous processes, the entropy of the universe goes up. And so one of the questions was to have you calculate the entropy of the system and then calculate the entropy of the surroundings. And then the last part was, well, is the entropy of this universe positive or negative? Well, if the system is positive and the surroundings is positive, then the universe is by definition going to be positive. Okay. If they're both negative, then the universe is negative. If one is negative, if the system is negative, for instance, and the surroundings is positive, or vice versa, and it's more positive than it is negative, then the universe is positive. Okay, very simple math right here, right? 2 plus 2 is a positive 4, right? Negative 2 plus a negative 2, negative 4. We talked about the Boltzmann equation and how this is used to describe what Boltzmann conceived of as microstates, the possible configurations of energy within matter, and in the relationship that matter can be oriented in space, right? And that molecules can move in different ways. They can move translationally, where they are going from one place to another. They can move vibrationally, which is what we discussed in the paper this week, looking at the vibrations of fluoride or fluorine molecules and using that to figure out whether it's a hydrogen bond or not, or rotational motion, where they move about their axis. Okay. And the more motion you have, the more types of motion, the more different microstates you have, which a microstate is just a snapshot in time. If you were to take a balloon of gas and take a picture of those molecules in some kind of orientation, each picture, there will be different microstates, right? The microstate is the snapshot. And the number of microstates is directly linked to entropy. The more microstates, the higher the entropy. Okay, the higher the randomness. What influences microstates and thereby entropy? Temperature, right? If you put heat into matter, what's it going to do? It's going to make the molecules move more. The more freedom of motion, the more possible microstates they can have. Volume, the bigger the matter is, the larger the amount of the matter, the more molecules are in there. And that can also contribute to more microstates. The number of independently moving molecules, right? All of these things. And if the container is bigger, it's going to give gas and water more room to move around. So any particular snapshot is going to give you more microstates than if it was a more confined space. All of these things lead to increase in entropy. And as you would imagine, if more freedom of motion leads to more entropy, then gaseous matter is going to have more entropy than liquid because it has more freedom of motion. Liquid is going to have more entropy than solid. Molecules move very little. What are other things that increase? Gases, yeah, liquid, solids going to liquids to gases, yes. The number of gas molecules. So if we go from a situation where we have 2 gas molecules down to 1 gas molecule, that's going to decrease entropy. Okay. If the molecular mass is larger, that's going to potentially influence an increase in entropy. All these things essentially come together to increase disorder of the universe. All right. This third law of thermodynamics, we just got to mention it, but it's kind of like a fairly straightforward concept that we're not going to belabor. But it's essentially saying that the entropy of a pure crystalline substance at absolute zero is zero. Okay, so that's just kind of giving us a benchmark for where entropy lies, right? Absolute zero is completely devoid of thermal energy. And so there will be, by that concept, no entropy, because entropy is related to heat, right? That's why this is a part of thermochemistry, part of thermodynamics. So a pure solid substance at absolute zero has no entropy. Once you increase the temperature, then you start bringing entropy into it. Now, here's a list of different substances, and then it gives you their respective entropy value. Now, notice for entropy, it's joules per mole Kelvin. Those are the units, okay? Not kilojoules. So when we're doing calculations with enthalpy, which is often kilojoules, right? We need to make sure and make that conversion when we put them together. And what you'll hopefully notice is a trend whereby as entropy increases, so does the molar mass of the substances, okay? And so, again, entropy is linked to not only the number of molecules, not only temperature and volume and microstates, but also the mass of the matter that we are looking at. Right? So when you get questions like predict what's going to have higher entropy, or is this going to be an increase in entropy or a decrease, a positive sign, a negative sign? Keep these things in mind, okay? These are ways that you can very easily predict the behavior of entropy without doing any calculations, okay? As entropy increases with molecular mass, it also increases with more complex molecules, okay? Why do you think that is? Why does methane have less entropy than ethane? And ethane have less entropy than propane? Any guesses?
The more complex the molecule, the more bonds and atoms there are going to be to have interactions which cause microstates.
Exactly. You're going to have more dynamic microstates the more bonds you have, the more possible vibrations, the more possible rotations, right? The methane, there are no rotations with that really, because there's just the one atom. But with ethane, let's see if I can do a little drawing here. With ethane, this methyl group can rotate this way, clockwise. This methyl group could rotate the other way, counterclockwise. They could both, rotate the same way. There's like Hannah said, there are more possibilities for these molecules to be arranged and to move. And the more possibilities, the more combinations, the more microstates, the higher the entropy. Okay, so let's predict which has more entropy. Sodium chloride or hydrochloric acid at room temperature? Which one's going to have more entropy?
Sodium chloride.
Yes. Why?
The larger molecule, because sodium's larger than hydrogen.
Yeah. Sodium has a higher molar mass than hydrogen. What about 2 moles of hydrochloric acid, gas, or 1 mole of hydrochloric acid, gas, at room temperature?
2 moles.
2 moles, right? More moles, more entropy. 1 mole of hydrochloric acid gas or 1 mole of argon.
Well, argon's a noble gas, so it doesn't really react too much, but also hydrochloric acid is a more complex molecule.
Right. So at least there's a hydrogen and a chlorine, and they're, moving around a little bit. The argon is just kind of by itself. It's not interacting with anything else. So it's really not nearly as dynamic. So not much microstates, not much entropy in relationship to hydrochloric acid.
I have a question. Like, how do you compare the solids and the gas? Because the first one was like sodium chloride solid versus hydrochloric gas.
Oh,
So wouldn't the gas have more?
sorry. Yes.
Great.
I missed that. Sorry. Yeah, you're absolutely right. So the hydrochloric gas is going to have more entropy than the sodium chloride solid. I thought they were both solid but that wouldn't make sense to have hydrochloric acid solid. So,
Okay. So like, just so even if, so like if we're comparing gases to solids, like even
Yeah.
if the solid is bigger and more complex, would it still have less entropy than the gas?
yeah, it's generally that's a good rule of thumb because they don't move around much by
Okay.
definition, right? The gas, even if it's a smaller, less complex molecule, is going to have much more freedom of motion. And so as a result, going to have more microstates.
Okay, that makes sense.
Yeah, thanks for pointing that out. I totally made the common error of overlooking the states that they were in. So thank you for catching that. Okay. Entropy positive or negative for A? Going from liquid to gas.
Positive because it's becoming more chaotic, essentially.
Exactly. What about B?
Negative, because it becomes one molecule and it turns into a solid.
Yeah, the double whammy, right? Not only is it going from 2 molecules to 1, but it's going from a liquid to a solid. What about C? Same thing, right? 2 molecules to 1. And you're also losing a gas, right? So you're going from a system that had gas and a solid to now a system that just has one solid. What about D? No phase change, all gases. What changes here?
It becomes one molecule, so it is a negative change.
Correct. What about this? A, what's happening there?
Positive?
1 to 2, positive. Freezing of liquid water, what happens there?
Negative.
Negative, right? Less freedom of motion. Solid to gas for C. I know you guys know this one.
Positive.
Positive. What about D? One to 2. Positive. Positive. I gotta make sure I read this one right. 1 mole of H2O liquid at room temperature. 1 mole of H2O liquid at 50 degrees Celsius. Same amount of moles, same molecule,
What's room temperature in Celsius?
25-ish,
Positive.
27. Positive, yeah, because we're putting heat into the system. The molecules are going to move around more. They're going to vibrate more, right? It's not boiling or anything, but 50 degrees Celsius is hot. 37 degrees Celsius is body temperature. So, all right. So that kind of gives you, there's the homework that I posted. We've brainstormed and decided that that is just optional. That is for your own benefit if you choose to take on some extra practice, but you don't have to do the homework that is posted to week 8. I haven't created an assignment for it. But if you did, you use this practice to kind of just predict how entropy is going to go based on the reactions, what's happening with the molecules, the numbers, the moles, the phases. And so that will help guide you. But now, what if we want to get more quantitative, right? We could say that entropy changes for a reaction can be estimated in the same way that we figured out enthalpy change. So we take the sum of the moles times the entropy values of the products and subtract from that the sum of the moles of the entropy values of the reactants. And that gives us the overall entropy change. Okay. And here, N and M are going to be the coefficients in that balanced equation. Okay, that's what we take into consideration for the moles. So with that in mind, I want you guys to try to do this. Here you have a balanced equation. Looks like methanol and oxygen going to carbon dioxide. Well, that's combustion, right? Look at the table. Look at the entropy values. Make sure you have the right phase, right? And see if you can calculate the overall entropy change for this. Remember.
Repeat, what were N and M? You said they were coefficients. What do you plug in for N and M? Are those moles?
Yes. So those are going to be the coefficients in the balanced equation. So for N, that's going to be the products. So it's going to be 2 for carbon dioxide and 4 for water. And the M is going to be the coefficients of the reactants. So 2 for methanol and 3 for oxygen. Okay. All right. So let's do that. See what we come up with. I say M. No, I said N for the first one.
What's like the practical application of an entropy calculation? Like I understand that it's basically how random or chaotic the system is, but like what do you do with that number?
Well, we'll get to that later.
Okay, fair enough.
minus. Okay, hopefully I wrote this correctly. We'll see. Get my glare out of here. So it's the sum of the products times their coefficients minus the reactants times their coefficients. So if you look up that chart, we want to do 2 times, what was this? This was carbon dioxide, I think. Hold on, sorry. 2 times carbon dioxide plus 4 times water, right? Because those are products, minus 2 times methanol plus 3 times oxygen. And these are just the values I got from that table. So if you add all that up, what do we get for that?
Negative 161.65.
161.65. And then, of course, our units are joules per mole K. Anybody else get something different? Okay. So, no, that's not what I want to do. Where did it go? Hold on. All right, guys, I gotta find my slide deck. It vanished on me. There we go. Okay. I have to exit out of that, get back in. Voila. Okay. So very straightforward, right? Same thing we did with enthalpy. How about this one? Balance the reaction and then calculate the change in entropy. So H2 gas and O2 gas into H2O. Well, it doesn't say. Let's just assume that's H2O gas also. So work on that, and then H2 gas, N2 gas into ammonia, and that's going to be all gas as well. Let's work on that, see what you get. All right, so first we have to balance this, right? How do we balance this?
Put a 2 in front of the hydrogen and in front of the water.
Yes. Great. 4 hydrogens, 2 oxygens. So then now we just look up those values for the product. So it's going to be 2 times what was the value? I'm now
130.6. Oh wait, for the product, I'm sorry.
yeah,
188.8.
188.8. Okay, minus let's do 2 times hydrogen gas.
130.6.
Plus 1 essentially times oxygen gas.
205.
Okay, and then you just plug and chug, right? And just let me know when you get the answer for that if you haven't already.
And you're subtracting those 2 on the right altogether, right? Not just the middle one.
I'm subtracting this from this.
Okay, great. Just making sure.
Yep.
Is it negative 88.6?
Okay. So what's the next one? H2N2 and NH3. So H2 plus, and that's gas, plus N2 gas yields NH3 gas. Okay. What do we need to balance this one? 3 here, 2 there.
A 3 in front of the H2 and a 2 in front of the NH3.
And then 2 here. Okay. Nope, that's not right. That's probably what you said. That's not what I heard. Yeah. Right? 6 hydrogens, 2 nitrogens. Okay. So then again, same kind of thing. 2 times whatever the entropy is for ammonia. So I can look here. What's ammonia? 192.5 minus the sum of the reactants. So 3 times hydrogen gas, which we said was 188.8 from above, plus 1 times nitrogen, 191.5. Okay. What do we get when we crunch all that? Anybody get that?
Yeah, I got negative 198.3. I think on the board we accidentally put the H2O instead of the H2.
Oh, shoot. Sorry, guys. Right here. Yeah, I did. That's going to be that should be 130.6. Right? Thank you. All right. Any questions on that? Like I said, it's just like enthalpy, so it should be familiar. Now, here's a diagram showing how entropy can vary with temperature, meaning that entropy and temperature are therefore related. Entropy is on the y-axis, temperature is on the x-axis. And as you see, entropy starts to go up linearly, and then it has a steep increase, and then goes again, and then another steep increase, okay? And so what we know about phase diagrams and stuff like that, or not phase diagrams, but the plotting of temperature and time, what can we infer about this? What processes are corresponding to the entropy increase? What's number one and number two? What's happening there, do you think?
Fusion and evaporation.
Yeah, phase change, right? Absolutely. So this is kind of the opposite of that plot we saw where it increases and then it plateaus and then it increases and plateaus. Here, it's increased and then it has a radical increase and then it increases more and then a radical increase. And that is, so let me change color to not blue, right? Solid, 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 liquid. And what do we know about entropy in liquid form versus solid form? We know that entropy increases in liquid because there's more molecular motion. All right, and then now it's liquid, 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 solid, gas, right? And what do we know about gas? That has even more entropy. So why is the entropy change for 2 larger than 1? I know.
Because the gas is more random than the liquid.
Yeah, absolutely. So what's happened is entropy is increasing as you're putting temperature into the system. And then you have that solid turn into a liquid. Now, all of a sudden you have a lot more microstates possible. So it jumps up and then it starts continuing to increase, but not as radically as it approaches evaporation. And once that happens, it's now a gas, which has way more molecular freedom than liquid and a solid. And so you're going to have a larger spike in that graph as a result. Okay. All right, so I'm going to take a pause here and go pick up the offspring. when I come back, I will record the rest of the lecture. Just be some more problems kind of similar to this, but then we'll get into Gibbs free energy. And then I'll post that to Canvas, okay? And we'll get into why entropy is important, why we even care about calculating this stuff in the first place, okay? So you guys all have a great weekend, and I'll see you Tuesday for the next phase being equilibrium, okay? All right, so long.
Thank you, Dr. Franz. Have a good day.
You too. Okay, I'm back. And so it actually didn't take too long. It's 2:14, so 2:15. So I could have probably just had you guys take a break. But anyway, this gives me extra time to continue the lecture. And so let's dive in to where we left off. And hold on a minute. Gotta get this all set up. So we left off with this graph. And we said that entropy has rapid increase as you go to these different phase changes, because entropy increases from solid to liquid to gas. And so that brings us to entropy's role in the universe, and Alia's question of, why is it important to calculate change in entropy? What's the significance of it? The universe, as we've talked about previously, is made up of the system and the surroundings and the properties of the system and the surroundings, right? Heat goes in between the system and surroundings, and how it does all totals up to the sum of the universe, okay? Whether it's enthalpy or energy or entropy, the universe is going to be composed of what's going on in the system and what's going on in the surroundings. And the reason that entropy is significant is because it describes energy moving in all the different processes of life and beyond life, right? Whether you're boiling water or melting ice, right? Or I don't know, making popcorn or dissolving sugar in water, like we've talked about. These examples. Making tea, wishing it was coffee. All of these things, cellular metabolism, right? Your body is not in equilibrium. Your cells are not in equilibrium. They go into disorder. And in order to maintain a low level of entropy, you have to feed the body. You have to resupply it with new forms of macromolecules, right? And vitamins. That is because entropy is at play. Entropy is, in some ways, considered a breaking down of things, right? As the energy leaves, the thing breaks down. And so by calculating the entropy, and what are the units of entropy? We said they're joules per mole times Kelvin. So entropy is just a measurement of energy, the amount of thermal energy in a given amount of something at a certain temperature, joules per mole times Kelvin. And by calculating that, we can determine whether or not the value is negative or positive. And if we know it's negative or positive, that tells us something about the state of the overall universe. Okay? And that's why it's important to know this stuff. If we know that there is a positive value of entropy or an increase in entropy in the system, and there's an increase in entropy in the surroundings, then that informs us about what's going on in the universe. Okay? If one is negative and one is positive, then it's a play, it's a battle to see which one is greater or has more value, right? And so we calculate entropy to inform us about what is going on in all of these different biological and abiological processes in terms of heat, moving, leaving, okay? So for instance, when we look at hydrogen gas and oxygen gas forming water gas, two different molecules coming together to form one. So that's going to decrease entropy, right? And as we see, it's a negative 88.6. Same with the other one. Hydrogen gas and nitrogen gas form ammonia gas. Two molecules coming together to form one, decreasing entropy, 198.3, negative. See? Okay. That tells us the state of the universe. Okay. That's why we do these calculations. We can see overall, is disorder and randomness increasing in this system and its surroundings, or is it decreasing? And what is that contribution to the universe? And remember, it's a state function, right? It doesn't matter if it is a combination of millions of reactions going on for billions of years, right? All that matters is what that initial entropy value is and the final entropy value. Entropy itself can't be negative, but change in entropy, delta entropy, is what can be negative, meaning it's decreasing. Okay? So what that means is that when we see an increase in the change in entropy of the universe, for some reason it's kind of hard for me to say entropy today. When we see an increase, we say that that is going to be a spontaneous process, right? The natural progression of things. If we see a decrease and entropy is negative, then that's a non-spontaneous process. And if we see that entropy is at 0, then we can say it's at equilibrium. It's not increasing its randomness, it's not decreasing its randomness. And equilibrium is what we're going to talk about next week. Okay. So for this problem, we have solid water going to liquid water, phase change. And we see the entropy change for the process is 21.1 joules per Kelvin and requires that the surroundings transfer 6.00 kilojoules of heat to the system, right? That number should look familiar. Is the process spontaneous at negative 10 degrees? Is it spontaneous at positive 10 degrees? Well, we should probably already know the answer to this based on what we know about water and the temperature we're given. But I would like you guys to try and work on this and see. Well, actually, you know what? I need to give you some more information before we can really solve this problem. So tell me, not actually, but tell yourself, what do you think it is? Do you think it's spontaneous at negative 10? Do you think it's spontaneous at 10? Remember, what is spontaneous? It's something that has to happen without outside intervention. So I'll give you a couple seconds to reflect on this. Does water melt at negative 10 degrees Celsius? No. Does it melt at 10 degrees Celsius? Yes. So if we were to do some calculations, we should see that the entropy at -10 should be non-spontaneous. It should be like a negative value. And at 10 degrees, it should be a positive value based on just common sense of how water behaves, right? So let's get into the next few slides. I got to give you a little bit more information. And if I can remember, we'll come back to this. And if not, remind me on Tuesday and we'll come back and we'll show definitively that that is the case, okay? That it does work out. Now, understanding spontaneity and determining whether a process is spontaneous is difficult because you need to know the entropy of the system and the surroundings, right? And oftentimes we don't have both of those together. And so we have to derive one of those by using Gibbs free energy, okay? Gibbs free energy is a property that uses the system's enthalpy and entropy to get at missing information, okay? And the way they do that is by saying, for instance, that let's say heat is flowing in or out of the system. And as it goes in, as it comes out, it's changing the entropy of the surroundings, right? If heat is going into the system, it's decreasing entropy in the surroundings, right? Vice versa. If it's an isothermal process, so if the heat is not different, if it's the same, if it's constant, then we can say that the entropy of the surroundings is equal to the heat of the system over temperature. Now, if you remember the first law of thermodynamics and what we talked about there, perhaps you'll remember that little derivation we did to show that the heat of a system can be set to as equal to the change in enthalpy at standard conditions when pressure is constant, okay? So that means we can substitute enthalpy in for Q. Now, if we say that the entropy of the surroundings is equal to a negative Q of the system over T, and we know that if the pressure is constant, we can say that Q is equal to delta H or enthalpy, then we can say, oh, and we also know, right, that the entropy change of the universe is equal to the sum of the entropy changes of the system and the surroundings. Then we can combine all these to get the missing variable. We could say that the change in entropy of the universe is equal to the change in entropy of the system plus a negative change in enthalpy, right? Replacing the enthalpy replacing the Q, the heat, with enthalpy over T. And then if we multiply both sides by a negative T, we get this last equation, okay? And so what's happening here? We are multiplying each side by a negative T. Right here and here and here, okay? So that's going to cancel out the T here. It's also going to cancel out the negative sign here. It's going to make this positive. And then you put that all together and you get a negative T times change in entropy of the universe is equal to change in enthalpy of the system minus, wait, no, sorry. I guess that's not right. Oh, no, that is right. Yeah. Sorry. That's right. I just switched around the T times change in enthalpy of system with the, or T, sorry. I switched around this one and this one, but it's right. So change in enthalpy of the system minus temperature times change in entropy of the system. Okay. This is when we are missing the entropy value for the surroundings. Okay. And you don't need to know how we went from here to here. You just need to know how to use this. Okay. So negative T change in entropy of the universe. That's this thing right here in the bottom right here. That is Gibbs free energy. That is what we call delta G. So if you look at that appendix G, you'll see the delta H, you'll see the delta S, and you'll also notice now a delta G. And those are going to, each molecule in that appendix is going to have different values for this. When the change in entropy of the universe is positive, meaning entropy is increasing, free energy is decreasing, is going to be negative. Okay. And so if we want to calculate delta G, so again, we're just replacing this negative T times delta S with a delta G. We just pop that in down here and we get delta G equals delta H minus T delta S. That's our equation. And again, look at the graph, because I think these graphs are nice to put things into context of how that all fits together. If the change in entropy of the universe increases, delta G decreases. And it's a spontaneous process. If the entropy is decreasing, delta G, or Gibbs free energy, is increasing. And that's going to reflect a non-spontaneous process. So nothing's changed here, right? Increasing entropy is spontaneous, decreasing is non-spontaneous. We're just now adding in another variable, delta G, and saying that it's the inverse. Unless, of course, delta S, or change in entropy, is equal to 0. There's no change. Then there's also going to be no change in the free energy. And again, that's going to be a state of equilibrium. Okay. So let's put this into practice. Okay. Let's use a standard enthalpy and entropy data from this appendix. I just put it here already, so you don't have to look it up. But to calculate the free energy, or the delta G, change for vaporization of water at room temperature. Okay. And then it says, what does the computed value for delta G say about the spontaneity of the process? In other words, is it spontaneous or non-spontaneous? Okay. So let's see if you can set this up. What you have to do is you have to find the delta H. How do we find the delta H? Well, we have those delta H values for liquid water and gas water. And then you do, products minus reactants, and same thing for entropy. So now we're doing the products minus reactants to get our delta H. We're doing our products minus reactants to get our delta S. And then we put it all together in this top equation, delta G equals delta H minus T delta S. And the T, of course, is at 298. So see if you can do this. I'm going to pause it and write some stuff on the board, and we'll jump back into it here. Okay, so hopefully you guys can see that. dark in here. Need some more light. Subject. So we know that delta G equals delta H minus T delta S. And they give us the values of liquid water, delta S, delta H being kilojoules per mole, negative 286.83, and the entropy, joules per mole Kelvin, 70. For gas, negative 241.82 and 188.8 for the entropy. So what do we need to do first? Let's solve for enthalpy. What do we know? How do we figure out enthalpy? We take products, the sum of the products minus the sum of the reactants. So what is the product? In this case, the product is what? The gas. So we want to put the gas first, product, so negative 241.82. Let's have our units, kilojoules per mole, minus negative 286.83 kilojoules per mole, right? And that should give us our delta H. See that? And then for our delta S, same thing. We take the product, 188.8 joules per mole degree, or mole times Kelvin, minus 70.0 joules per mole times Kelvin. And so we do that. Let's see what that is. Don't have my calculators with me. Got to do it myself. Okay, so negative 241.82 minus a negative 286.83, getting 45.01. And that's going to be kilojoules per mole. And then for entropy, 188.8 minus 70.0, 118.8, right? Okay. So, and that's going to be joules per mole K. So now we just plug these two numbers into this top equation here. And we get, so delta G is going to equal delta H, 45.01 kilojoules per mole, minus, and then we want to get our temperature, 298 Kelvin, times 118.8 joules per mole K. Now, one thing that we have to consider is that we have kilojoules here and joules here. So let's just convert this to kilojoules by taking times 1 kilojoule over 1,000 joules. That will give us kilojoules. And then we just plug this all in. So .1 minus Okay, I've got 9.6. And that's going to be kilojoules per mole, right? Because the Kelvin cancels. So that's a positive number, right? What does that say about the spontaneity? It's going to be not spontaneous, non-spontaneous. So let's go back to the slide deck. Well, here, wait, let me let you look at this for a minute. Okay. You can pause it if that wasn't enough time. Yeah, so delta G is greater than 0. So it's 9.6, so it's non-spontaneous. So here's another problem. They give us the enthalpy of vaporization, Gibbs free energy equation, and then they want to use the values to the right to calculate delta G for the reaction above. Again, it's liquid going to gas. And they say that the reaction is going to be at 25 degrees and then calculated at 125 degrees. So we have our S values, or our entropy values, and we have the delta H already. So we'll pause here. I'll write some stuff and see what you come up with. Remember, you already have delta H, so that's good. All you need to do is solve for delta entropy, change in S, and then plug it in, and then use the 25 degrees Celsius, convert to Kelvin, and then just pop that out, pop in the 125 degrees converted to Kelvin, and then get your answer. There. Okay. Okay. I decided I'm just going to write it out with you guys. It's not much to write out this time, but hopefully you use that pause to pause yourself and work on this on your own. But so we have delta G equals delta H minus T delta S. We can say delta G equals delta H, which we have 44.01 kilojoules per mole, which I think we calculated 45.01 in the last problem. So one of those numbers must have been off, right? Anyway, we got that. And now we need to figure out delta S. So it's going to be product minus reactant. Product is gas, and gas is 189 joules per mole K. Minus reactants is, where is it? Hold on a minute. 70. I should have known that because we just used that recently, the last problem. Okay, and that's going to give us our delta S. And then, yeah, so they rounded this up from 188.8 to just 189. Okay, so it's going to be this minus, what's the first one? 25 degrees. So 298 times, what's that? 10.01 joules per mole. Okay. No, that's not right. 13. And let's calculate that out. Get out of the way. So 44.01 minus 25, or no, this should give us the same, pretty much the same answer, but that's just 44.01 minus 8 times. Oh, and then, right, we got to times 1 kilojoule, 1,000 joules. At 8.5. Okay. Which our last answer was 9.5 or something like that. And again, that's because we calculated 45, which must be off from something. Now let's see what happens when that goes from 100. It's going to be 398. So let's do delta G equals 44.01 kilojoules per mole minus 398 times 119.01 joules per mole, K times 1 kilojoule over 1,000 joules. I think it's probably going to be just a factor of 100. 1 minus, oops. .3.4 point. Let's do 0.36. Okay. That should say 47. That's a bad 4. But it's getting kind of late in the day, and I have not had my coffee, and so bear with me. But you see that the delta G is higher at a higher temperature. Okay. And what is a positive delta G? If we go back to our slide deck, if delta G is greater than 0, it's non-spontaneous. Now, liquid going to gas at 25 degrees Celsius at room temperature doesn't happen as much as it does when you increase the temperature, right? Now, 125, you're boiling. Okay. So that's the relationship of delta G in the context of this phase change when we just have the system and we don't have the parameters of the surroundings. Okay. So here's another problem. For the reaction below, calculate the standard free energy at room temperature. Using the standard free energies of formation, the standard enthalpies of formation, and standard entropies. Okay. I'm sorry, standard free energies. Yeah. Do the results indicate the reaction to be spontaneous or non-spontaneous under standard conditions? Okay. So here we have our delta G values, our delta H, and our delta S. And what they want to do, what they want us to do, is to calculate the free energy of this reaction. And based on that calculation, determine whether or not it's spontaneous or non-spontaneous. Okay. So let's have you guys work on this, see what you can come up with. Remember, moles times the sum of the moles in the products minus the sum of the moles times the reactants for all of these. Let's see what you get. Okay. Okay, so to calculate delta G, we look at those values. If we go to that slide again, we see that delta G is for mercury oxide is negative 58.3, and then 0 for mercury and 0 for oxygen, right? So products minus reactants. Product being mercury and 1/2 oxygen. So we take one, here, let me stop sharing. We take 1 times 0 plus 1/2 times 0 minus the sum of the reactants, 1, because the coefficient is 1, times a negative 58.43. Well, 1 times 0 plus 1/2 times 0 is 0. And 0 minus a negative 58.43 is a positive 58.43 joules per mole. Okay. Right? Or I'm sorry, kilojoules per mole. I'm thinking entropy. And that tells us everything we need to know, right? Let's go back to that slide. If delta G is positive, it's non-spontaneous. Where was that? Here, delta G greater than 0, non-spontaneous. Bam. But we're not done, because it says using the standard free energy of formation, that's what we did, and then the standard enthalpies and entropies. Okay, so now we got to do that second part where we now add up the entropy and the enthalpy and see if it equals the same as this number, right? So let's do enthalpy. Change in enthalpy is equal to products minus reactants. So again, mercury is going to be 0 also. So 1 times 0 plus 1/2 times oxygen is also 0. Okay, so that makes it easy. And we have 1 times a negative 90.46. Yeah. Okay, it's got those values from the delta H. One times 0 plus 1/2 times 0 is 0, and 0 minus a negative 90.46 equals a positive 90.46. And it's enthalpy, so the units are going to be also kilojoules per mole, I think. call. Okay. And then we go and do our last but not least, entropy. Oh, let's see what those values were. Entropy for mercury, 1 times 75.9 plus 1/2 times 205.2 minus 1 times 71.13 . Now we got to actually use the calculator. I can't do that in my head. So let's do 5.2 plus 0.3. I'm getting a 107.4. And it's entropy, so this is joules per mole K. Okay? Okay. Let me stop sharing so you can see that. Okay. So we have our delta H and we have our delta S. We plug it into that equation. Delta G equals delta H minus T delta S. Okay, and that would be equal to 90.46 kilojoules per mole minus, what was the temperature here? I think it was 298, but let me just, 298. Okay. Minus 298. Let's put in that 0.15 to be specific. Times 107.4 joules per mole K times 1 kilojoule per 1,000 joules. Let's see what we get. 90.46 minus 4. Okay, for that, I've got, what did I do here? Hold on. I did not get the 58.43 that I was looking for. Let me try that again and see what's going on. 90.90.46 minus 298.5 4. Oh, I just forgot to hit equal. I forgot to hit equal, but when I did, I got 58.43869. 58.43 is good enough kilojoules per mole, and we validated it 2 different ways. Voila, bam, we're done. Okay, I'm not going to get into the next couple slides. There's one slide that gives you more practice calculating the delta G, given looking up values in Appendix G. And then the other one is kind of looking at exceptions to the rule, but I don't really want to go over that, not being face-to-face. So this, I think, is kind of a great way to end, because we show that we can validate free energy in two different ways, right? And that it all adds up in the grand scheme of things. So I'll stop there. Again, practice these problems. Practice makes permanent. If for whatever reason I had some typos, let me know. I think I did everything okay. But review this, and if you have any questions, talk with Erina, Sean, or me, and we'll get through this, okay? Next week, we're going to start something new. We're going to go into the next chapter on equilibrium. But again, it's tied into this. Everything builds on itself. Okay, I hope you guys have a great weekend. Stay safe, and we'll see you next week.